Here I'm going to present and apply something called the Squeeze Theorem. We'll see a proof of it in a later video. The Squeeze Theorem states that if I have three functions, f, g, and h, they're all functions of x, such that f is smaller than g and g is in turn smaller than h, smaller than or equal to, I should say, on some interval containing a, except possibly at a, and if as x approaches a, f and h share a limit, we'll call it L, then the function in between the two is going to have the same limit. What? All right, we're going to see what this looks like visually. Suppose here I have some function f, and then I have some function h. I need to adjust this just a little bit. Okay. And at a point A, the limit, you know what, I'm going to get some different colors. Hang on. There. So f is the blue one down here. H is the purple one up here. So we can see that h is at least as big as f on some interval. I don't care what's going on over here or way over here, way far away from A. What I care is what's happening near A. And we'll say that at A, the limit is equal to L. Now let's say that we have some function g that on some interval containing a is between f and h. So g can do all kinds of weird stuff, but it's between f and h. So there's my g. Then it must be the case that as x approaches a, g has a limit of L. Visually, it should make perfect sense. We don't care what's actually happening at A. Any of these can have a discontinuity at A or a little hole in the graph. Makes no difference at all. We're talking about how the graph is tending as x approaches A from the left and from the right. In a nutshell, that's the Squeeze theorem. Now let's see how this is applied. We are asked to find the limit as x approaches 0 of x squared times the sine of 1 over x. You may recall that as x approaches 0, the sine of 1 over x wildly oscillates. And in case it's helpful, here's a reminder of what the graph of y equals the sine of 1 over x looks like. It's trying to be everything between negative 1 and 1 as x approaches 0, right? So what I don't get to do, so a big ol' I don't get to do, the limit as x approaches 0 of x squared times the limit as x approaches 0 of the sine of 1 over x. That's the product law for limits. But that, as you may recall, only applies if the limit as x approaches a of f and the limit as x approaches a of g both exist. Then I can find the product of the limits. But here, we have a situation in which this limit does not exist. So I don't get to apply that limit law. What we're going to do is we're going to apply the Squeeze theorem. First, I want to analyze the sine function a little bit. Let's just consider the sine of x. We know that the sine of x has a range that goes between negative 1 and 1. No big deal there, right? Suppose I multiply this entire inequality by a 3. 3 times the sine of x. Well, that's going to have a range between negative 3 and a 3. And in trigonometry, you called that changing the amplitude. Well, I can in fact multiply all three parts of this inequality by any positive value. And in this case, see what we have is x squared times the sine of 1 over x. I can multiply all three parts of the inequality by x squared. So here I'm just multiplying by x squared times the sine of x, and that's going to be between negative x squared and x squared, right? So x squared right here is just playing the role of 3. So those are just some facts about the sine function. But we're not concerned about the sine of x. We are concerned about the sine of 1 over x. But it's still true, you can see it here, that the sine of 1 over x is between negative 1 and 1. So what I'm doing is I'm starting with a known fact about the sine function. What I would like to do is I would like to build this expression here, the limit as x approaches 0 of x squared times the sine of 1 over x. And I'm starting with just something I know about the sine of 1 over x. Now, I'm building up this expression here, and so I'm going to multiply all three parts of the inequality by x squared. And according to the discussion that we just had, I know that x squared times the sine of 1 over x is going to be between negative x squared and x squared. And in terms of building the expression, I have sine of 1 over x that's being multiplied by x squared, so everything's cool. And there's a property of limits that I haven't talked about, but should make intuitive sense. It says that if I've got two functions that are in a particular order, like one smaller than the other, then the limit of the smaller function won't be bigger than the limit of the bigger function. In other words, I can take the limit of all three parts of the inequality. And it's the limit as x approaches 0. So the limit as x approaches 0 of negative x squared should be less than or equal to the limit as x approaches 0 of x squared times the sine of 1 over x, which is in turn less than or equal to the limit as x approaches 0 of x squared. Just barely squeeze that in. And in terms of the expression that we're building, we started with the sine of 1 over x, and then we multiplied by x squared, and then finally we took the limit of all three parts of the inequality. Now, the limit as x approaches 0 of negative x squared, well, I can directly substitute. That's a 0. And likewise, the limit as x approaches 0 of x squared is 0. I know that just by looking at it, right? In between 0 and 0, I have the limit as x approaches 0 of x squared times the sine of 1 over x. So you may see what the conclusion is, but I'm going to back it up just a little bit here. Folks, I have here a function that I'm going to call f, and f is equal to negative x squared. And that is always less than or equal to, say, h, which is x squared, right? X squared is never negative. Negative x squared is never positive. They agree at 0, but that's not a big deal here. And we have squeezed a function g, x squared times the sine of 1 over x, in between f and h. The limit as x approaches 0 of f is 0. The limit as x approaches 0 of h is 0. It then follows by the squeeze theorem that the limit as x approaches 0 of x squared times the sine of 1 over x is equal to 0. If you're not really sure what we've done, let's look at this graphically. I talked about a function f that we said was negative x squared. So here I've graphed y equals negative x squared. And then we can consider y equals x squared. I'm going to spread this out just a little bit to make it a little better for us to look at. So as I said before, y equals negative x squared is never bigger than y equals x squared, right? So those are our f and h, if you like. Now, suppose I consider y equals the sine of 1 over x. Now, clearly that thing is not in between y equals x squared and y equals negative x squared. But this isn't what we were after, right? Remember, that function is between negative 1 and 1. What I'm going to do here is I'm going to multiply that by x squared. And then we're going to zoom in a bit. In fact, I'll get rid of that. And we'll see what's happening here. I have right here x squared times the sine of 1 over x, and it's between negative x squared and x squared. You see? And so if I just get rid of these two, then you can kind of see where the parabolas exist here. And what we've done is we've squeezed x squared times the sine of 1 over x between negative x squared down here and x squared up here, right? So it's the squeeze theorem that's allowing us to make, to draw a conclusion about a limit based on the order of the functions that we have. So I'll just recap. We wanted to build the limit as x approaches 0 of x squared times the sine of 1 over x. I started with just the sine function. I know that the sine of anything is between -1 and 1. Then I multiplied all three parts by a positive value, x, or a non-negative value, x squared, right? The reason I chose x squared is because that's the coefficient here inside the limit statement. It's the limit as x approaches 0 of x squared times the sine of 1 over x. Then I applied the limit as x approaches 0 to all three parts of the inequality. And I made a direct substitution where I could, which then put the limit as x approaches 0 of x squared times the sine of 1 over x in between 0 and 0. So by the Squeeze theorem, our limit is equal to 0. If this is on a test, and it probably will be in my class, then writing down limit right here is essential. Writing down the words by the Squeeze theorem is essential. In fact, except for the different colors that I gave you here, everything that I'm putting in this box, starting with the first inequality from -1 to 1, all the way to, by the Squeeze theorem, the limit of x squared times the sine of 1 over x as x approaches 0 is equal to 0. Everything in this box here, it would be required for you to get full credit for this exercise.